Hello, my name is Nantambi Melissa, and I'm going to be presenting our slides for the contextual acoustic AI for generating Luganda folk music from stories and moral narratives. So I'll be explaining more on the keywords for this project. We have a large acoustic model, and this is simply a deep neural network that's trained on large sets of audio data, and it's able to generate audio that captures the acoustic features of sound. Then context-aware music generation. In our project, we mean that the music composition of our system is based on a moral theme, and that's the context. Then acoustic embeddings are the numerical representations of audio features so that the computer can understand them. Then cultural preservation is maintaining and protecting a society's cultural heritage. And in our case, we are doing this through the folk songs. Then Luganda folk music. This is the traditional music played in the Buganda culture, and it's played for different purposes. Then oral tradition is the culture that's passed down by word of mouth, and storytelling is the cultural activity of sharing stories. We reviewed various previous works that have been done that align with our work. And for example, the system iComposer, which also generates music and also MuseFlow, but they have limitations of being limited to genre music and Chinese music, which don't apply to our sense. We also reviewed various papers that talked about music generation and generative AI, and these had limitations of focusing mainly on the Western world and not necessarily putting emphasis on cultural preservation. The main application problem for us is the loss of oral African tradition, particularly in Buganda. The new generation is not able to access them because they are not modernized. So we aim to preserve those oral parts and make them accessible. The computational problem that we are solving is generating culturally authentic Luganda folk music from moral narratives via cross-modal modeling in low-resource conditions, particularly here in Buganda. We learn a function that maps narrative text, moral themes, and style constraints to lyrics, melody, rhythm, and timbre, and the result is a context-aware, culturally structured folk song. So currently, most generative music models lack cultural conditioning, especially for African cultural music. They also ignore the tone bearing that comes with the African languages. And then they also use weak semantic condition instead of moral cues. Hence fail to link moral tension in text with melody contour changes. And also the main problem is data scarcity. Our model tends to build on these current computational solutions, that is music generation through lyric emotion analysis, as well as fine-tuned language models. Our objectives are to create a data set of both text and audio, which is specific to Luganda cultural narratives and folk music. Then we perform exploratory data analysis of the folk stories and the local music we obtained. And then we evaluate the output of the model for coherence and thematic consistency. And then we propose a framework for sustainable deployment of low-resource, culturally grounded AI systems in African contexts. The questions we ask ourselves are, what architectural components are necessary to compose both lyrics and melodies while adhering to linguistic and musical constraints of Luganda folk music? Then how can our model be deployed in a constrained setting without losing the quality of generating music? And then how can we ensure that the generated music remains culturally faithful? And additionally, to what extent does rhythmic variation of a song reflect changes in the narrative structure of the lyrics? Our research contributions, we created an audio data set from different culture songs from the Buganda culture from our sources. And then we created a text data set made up of Luganda folk stories. We also created a function that utilizes the Emotify music dataset and the J-Hartman model and assigns each verse an emotion. Each verse in the song lyrics are an audio feature based on the emotion. Then we're also able to generate lyrics for a folk song generated by one of our models, and it was conditioned on a moral theme. So the methodology of our system is a multi-agent architecture, and it works together to produce the final output. So it starts with input, and a user inputs a moral theme. This moral theme is processed and is input for the story generation model, which is a fine-tuned large language model, and it produces a story based on the moral theme. This is then input for the lyric generation module, which is as well a fine-tuned large language model, and it converts this story text into lyrics. Then these lyrics are go into emotion and audio feature mapping, where each line of the lyrics is analyzed for emotion and corresponding audio features are assigned to it. These audio features are then input for the music generation model, which will produce instrumental music basing on those audio features, and these will correspond with the lyrics. After the audio has been produced, we go into post-processing where denoising is done, and then our lyrics are then translated to Luganda using a sequence-to-sequence model. And finally, our output is a completed song package of lyrics, audio, lyrics in both English and Luganda, and then the story as well. And with user feedback, we can keep on improving the system. So our system, as I said, has a large language model, and this is the architecture for the large language model. The moral theme is input and tokenization is carried out. We then move on to the embedding layer, which converts these tokens into something that it can understand. And these are the word embeddings that go into the transformer block, which can have n number of layers. In this transformer block, root mean square normalization is carried out on the input. We then go into the multi-head self-attention layer. And then after that, we go into residual connection, where the input of the multi-head self-attention layer as well as the output are combined. We then go to root mean square normalization again. And then after that, that is input into the feed-forward network, after which residual connection is done again. This process goes on for n cycles for the n layers of the transformer block, after which root mean square normalization is carried out. Then we have a linear function, then a softmax function, after which we can have our final output. For the architecture of the conditional variational encoder, we have input of the condition, which in our case is the instruments, as well as the spectrogram, which are input into the encoder. After this, they are put into the decoder, of the conditional variational autoencoder. Then after this, after the decoder has matched the original input while respecting the conditional label, its output is reconstructed into a spectrogram, and this spectrogram is then converted back to the audio waveform from which we get our audio output. Our dataset description, we had 35 folk stories from the Buganda culture, and we got this from transcribing YouTube videos as well as a folk storybook entitled The Flame Tree. We also had an audio dataset of about 17 instrumental audios, and we obtained this from the School of Performing Arts and Film at Makerere University. We also had story lyric pair datasets, and these were 5, and also the Emotify dataset, which was used for emotional analysis. And these are some of the outputs from our EDA. From here, we can tell that the most common theme in our stories was wisdom, then obedience and cleverness, caution, and so on and so forth. We also found out the number of themes per story, which you can see from here, and also the distribution of storyline. We also carried out EDA on our audio dataset, and from this we can see that the xylophone was the most dominant instrument in all of the audio recordings that we had. And then this was more audio output, audio EDA for the audio dataset. And from here we can see that the audio features that we used were spectral centroid, we have spectral roll-off, zero crossing rate, which means square energy and duration of the audio per second. Then these were the waveforms for the different audios that we had. And this was EDA that we carried out on the emotified dataset as well, classifying the different emotions that we had in that dataset. And this is the output for from the model after story generation. We input the theme of cleverness, and this was the story that was output. And from this story, we see the lyrics that were output. Then after these lyrics were analyzed, and audio features, which you can see on the right, were assigned to each line of the lyrics. And these lyrics were translated into Luganda, as we can see here. Then we also had our audio, which was produced from the variational autoencoder. So the results from training, we observed that the reconstruction loss had a steady decrease, and the KL divergence gradually increased to around 60 to 80. And this is typical VAE behavior. And then, as I mentioned, we carried out denoising. And after we had produced the music, we used spectral gating to remove the noise from the output audio. And this is the before and after. And then with regards to model selection, we trained two models, one at 3 epochs and one at 5 epochs. And we decided to go with the model at 4 epochs because, as you can see from this graph, beyond that, validation loss was increasing. So we went with the one at 5 epochs. And then we used the fine-tuned llama model because it had lesser values of test loss and perplexity as compared with the untrained llama model. So for the demonstration of our developed product, as you can see from here, the user would input their moral theme and they would get an output of story, lyrics in both English and Luganda, as well as the audio. Yes, so our IP assets, we came up with the moral to melody mapping algorithm, and then also the modular multi-stage architecture with the 4 different stages, as well as the Luganda cultural corpus. The limitation we faced were limited size of our dataset, and then also denoising removes some part of the instrumental sound as well. And then the submodules are highly interconnected, and output quality of the previous model affects the next. And then assigning each verse in the lyrics an emotion without first considering those before or after can lead to misleading results. In conclusion, this project presented a context-aware Luganda folk music generation system that transforms moral narratives into culturally inspired songs. But the work is limited by data scarcity and propagation of errors to the architecture. Future works should focus on building larger size data sets, improving multimodal alignment and optimization for development, and should also carry out human in the loop production in their work. Yes, we would like to thank the Department of Performing Arts and Film for providing us with data that we use to make our data set. Thank you for your time.